here to the first law here of what? Thermodynamics. All right. Now, the first question we ask here, what basically is thermodynamics? Now, the definition here is that in the general sense of thermodynamics, it is the study of energy and its relationship to the properties of matter. All activities in nature involve some interaction between energy and matter. Thermodynamics is a science that governs the following: energy and its transformation. Feasibility of a process involving transformation of energy, feasibility of a process involving transfer of energy, equilibrium processes. So thermodynamics here touches every aspect here of our what life. It's an extremely important topic, and a lot of work here has in fact been done here on thermodynamics. Now, if we look at some areas of application here of thermodynamics, you people here are engineers, studying here to be engineers. I know it is very important here in the engineering field. Now, all natural processes are governed by the principles of thermodynamics. However, the following engineering devices are typically designed based on the principle of thermodynamics. We have here our automotive engines. Everybody here driving a motor car use it here for some transportation. And the principle here behind it, or the operating principle here, actually deals with what? Thermodynamics. We have here turbines, we have compressors, pumps, fossil and nuclear power plants, propulsion system for aircraft, separation and liquefaction, plant refrigeration, air conditioning, and heating devices. Now, all these things here actually deal here with what? Thermodynamics. All of this here. And unfortunately here, our mechanics here, you see they don't know here a lot here about what thermodynamic and thermodynamic processes. Other things here which people here who know a bit about motor cars. When a motor car here typically here goes to the mechanic for the first time, come from England or come from Japan or whatever, what they basically do here is that they go in the car and they pull out the thermostat and they dash it away. Because condemn thermostat is not needed in hot countries like Jamaica, but that is foolishness. Because the automobile engine here works on thermodynamic process, and the engine here, the temperature here affects the efficiency here of what? The engine. Now, when you remove that thermostat here from the engine here persistently run cold. Number one, it drinks more gas, and the engine actually wears a lot more. So it costs you a whole lot. But since our mechanics here, we have to sue them. They haven't been to school. They have not studied any thermodynamic systems. So they basically here don't know any better. In their mind, they're actually doing what? A good thing, because they are making the engine here actually run what? Cooler. In their mind, if the engine run cooler, it actually what? Lasts longer and it's better. But that is so far from the truth. As the scientists will tell you here, that the process here for the internal combustion engine is that it is more efficient here at what? A higher temperature. And the only reason here why engines don't operate at much higher temperature here is just due to the limitations here of the materials here in the engine. Most engines here operate region on 90 degrees, 90 odd degrees. When engine begin to overheat, you're talking about 110, 105. But they have made some engines now which are operating at 110, 115, and these engines here are much more what? Efficient. So the efficiency of the engine actually depends on what? The temperature at what the engine is operating. That actually comes from what? Thermodynamics. Now, the principles of thermodynamics are summarized in the form of a So here we have here our four law here. We have the zeroth law, first law, second law, and we have what? The third law. As I said here, what we are going to be looking at here is basically here some simple application here of what? The first law here of what? Thermodynamics. Now let us look basically here of what all these laws here are in fact what? Dealing with.
So, sir, that means that we won't be touching entropy at all then?
No, sir, yeah, we won't be touching entropy, yeah.
Okay, all right.
Second law, right, yeah, we won't be touching that, all right. So we have here basically here the zeroth law. And this law here actually deals with thermal equilibrium and provides a means here for measuring what? Temperature. All right. First law, the one here which we are going to be looking at, deals with the conservation of energy and introduces here the concept here of what? Internal what? Energy. So what we are going to look at, we're going to state the first law, write some equations here for the first law, and basically here look at the application here of what? The first law. The second law here provides with the guidelines on the conversion of internal energy of matter into work. It introduces here the concept here of entropy, which somebody mentioned here, which we won't be looking at. And the third law here defines the absolute zero of entropy, the entropy of a pure crystalline substance at absolute zero is in fact what? Zero. So we won't look at those. We'll just basically here look at what? The first what? Law. Now we have this concept here of thermal equilibrium here, which actually comes here from what? The zeroth law here of thermodynamics. And you must have an appreciation here of the zeroth law to appreciate your temperature and the reason here behind temperature, how temperatures here are in fact what? Measured. Now thermal equilibrium is an important concept in thermodynamics. When two systems are in thermal equilibrium, there's no heat transfer here between them. This occurs when the systems are at the same temperature. In other words, systems at the same temperature will be in thermal equilibrium here with each other. So that here's what the zeroth law here basically states. Two systems here are in thermal equilibrium. Then it means here that our two systems here will be at what? The same temperature. And that is the concept here that we actually use here in order what? To measure what? Temperature. Take a thermometer, stick it into some water. Thermometer here basically here gives us what? A reading. Okay? Now, what we are basically assuming here is that, look, there's thermal equilibrium here actually set up here between the water and what? The thermometer. So since we have thermal equilibrium here between the water and the thermometer, it means here temperature of the water here must in fact be equal to what? The temperature here of our what? Thermometer. So that here is basically here what the zeroth law here actually what states. And it's the basis here on which temperatures here are in fact what? Measured. Now, we talk about here now our thermodynamic what? System. Let us look at this simple system here. We have a pot, and we have some popcorn here in the pot. We apply heat here to the pot. What we notice here is that what? Popcorn here actually begins to what? Expand. So we're actually now adding heat to the system. All right, so when we add the heat here to the system, we get two things here actually happens. With an increase in the thermal energy here of the system, it actually gets hotter. So we actually get an increase in thermal energy. And two, the system is doing work, and that is manifested here in the lifting here of what? The lid of what? The pot. Remember here, work here is actually equal to what? Force times distance. So you're actually now moving thing a particular distance, or you're actually what? Doing what? Work. All right, so we're adding, so this now is our basic what? System. And we're adding heat here into our system. Now the heat here actually goes into what? Increasing the internal energy here of what? The system. The popcorn is going to get what? Hotter. So internal energy here will in fact what? Increase. And we also find here is that the lid here basically what? Lifts. So what happens here is that the popcorn here is actually what? Doing what? Work. It is actually expanding. It is actually what? Doing what? Work. Now, look at now what we mean here by what? A thermodynamic what? System. All right. Normally here we have a system here, and we normally put a boundary here around our system and say here, this here is basically our system. We don't want it here to be open. So what we see here is that the system can exchange mass and energy. So the boundary here with what? The environment. So basically with our system here, what we can in fact exchange is that we can actually interchange mass, or we can in fact what? Interchange what? Energy. An example of a closed system is that no mass flows, right? And the gas confined here to what? A cylinder. Gas here confined in our cylinder. Then what happens here is that since no mass here, gas actually leaves the cylinder, then no mass here actually what? Flows. And the boundary is actually now in this case the wall of our what? Cylinder. So this here could in fact be here our what? System. We have here some air here confined by a piston here in a cylinder. Now we have some definitions here that we should in fact what know. One of them here is actually an isothermal here process. So we have these various processes here that we actually have. One of them here is actually the isothermal process. And in an isothermal process here, what happens is that the temperature here does not in fact what? Change. All right. So if we should have a gas here in a cylinder with a movable piston, and we in fact plot a graph here of pressure against what? Volume, we know here that we will actually get these what? Curves. And we know here that Boyle's law here that actually what governs this behavior here with that is actually pressure and what? Volume. And what you notice here is that we actually get these things that we call here isotherms. And the isotherms here which are higher are actually the ones here at what? A higher what? Temperature. So A1, B1 here will actually be at a lower temperature than what? A, what? B. And this here actually in an isothermal process. So in this isothermal process here, temperature here is constant. The temperature here basically here remains what? Constant. Now, for us here to basically have an isothermal process, we assume that the system here is in contact here with what? A heat what? Reservoir. Now, in physics here, we have this concept here of things here which are in fact what? Reservoirs. Okay? So what it means here is that for the heat reservoir here, what we are basically saying here is that it can lose a certain amount of energy. Similarly here, it can in fact what? Gain a certain amount of what? Energy. And it will not in fact what? Affect what? The reservoir. The reservoir here has an infinite amount of what? Heat that it can give up any amount of heat. Similarly here, it can absorb any amount of what? Heat. In general, we assume that the system remains in equilibrium here throughout what? All what? Processes. So if the system here is basically in equilibrium here, the temperatures here are not what? Changing. Now we also have another process here that we actually call here now the adiabatic process. And in our adiabatic process here, what we have here is that we have no heat actually enters or exits the system. No heat actually flows into the system here, or no heat here actually what? Flows out of our what? System. Now here we have here our thermodynamic what? Systems. Now in thermodynamics, processes change occur in state of a what? System. Now the only thing here we have to be careful here is actually what? The signs here that we actually use here when we're in fact here looking at our what? Problem. So we have to be careful here about the signs. So Q is positive here, heat flows what? Into a system. So if Q is positive, it means here that heat actually enters the system. Similarly here, if Q is negative, it means here that heat actually will in fact be leaving here our system. Heat will in fact be flowing out of our system. Now we have here work done by what? System. Now for this work here is that we can have work done by the system or work done on the system. We'll look at that a bit later, and that's an important distinction here that we must make. That the work done by the system as opposed to the work done on the system. For this here, the signs here are basically what? Opposite. All right. So what you are saying here is that for expansion here, the work done by the system here is actually what? Positive. Right. So like in our example a while ago here with the popcorn here, is that it actually expands. So the system here actually what? Does work. So the work that the system does now will in fact be what? Positive. And work now is negative for work done here on our what? System. All right. So we have heat is positive when it enters the system. Work is positive when it is done by the system. All right. Negative when it is done on the system. Negative here when it actually what? Leaves our what? System. Very important here distinctions. I think these are the only distinctions here we need to know here when we're in fact looking here at what thermodynamic systems here and our first law here of what? Thermodynamics. Now let us look at what the first law of thermodynamics here basically what says. And the first law of thermodynamics here is basically a statement here of the law here of what? Conservation here of what? Energy. And basically here now, what the law of conservation of energy here is basically saying here is that what? Energy cannot be what? We can create energy, we can destroy energy. All that we can basically do here is that chain energy here from what? One form here to what? Another. So you see here, one of the things here that say here when people talk about here, we have what energy what crisis in that we're in fact running out of energy. We're not running out of any energy now because we have the same amount of energy here that we had before. We're not actually running out of energy per se. What we're in fact doing here is that we are actually converting the energy that we have into forms here that we can basically here what use. So we have the energy, but now we convert it into forms here that we can basically here what use.
And use it to move the car and everything.
Right. But the problem here that we have here is that we say we basically here are running out of oil. You run out of oil here because oil is the energy here that we basically use. But all the oil here that we basically use here, the energy here actually goes into heat, light, and what sound. So we just have to go and put it in a form here that we can basically here what use. All right. So we're not basically here running out of energy. We're in fact running out of usable what energy that man has the ability here to actually what use. All right. So but what we mean here is that the amount of energy here within the atmosphere, within the Earth or the universe here is basically what constant. But what we are doing here is that we are actually what heating up the planet. And what we are doing here is that we are actually converting here a lot of the energy here into what heat. So we're not destroying it. So the planet here is basically what getting what hotter. All right. So what we need to hear is that we actually need now to cut down here on the amount of heat here that we are actually putting in the atmosphere. So therefore here the planet here will in fact get what a much what cooler. Now I read a thing here in the papers here yesterday that England here has planned by 2030 here is that they actually plan to ban the internal combustion what engine, right? So they'll say at that time we are going to be putting a ban here on what the internal combustion engine, because the internal combustion engine here is actually the driver here for a lot of our what pollution.
So sir, they're going to go electrical.
Yes, sir, that's what they are saying is electric. We are going is actually electric. So what they are saying in 10 years time here, we're not going to have no more of our internal combustion engine. What we're going to have here is strictly what electric what cars. Strictly electric cars here we basically are going to be having, because internal combustion engine here is in fact what a very what big what problem. All right, so if we can get rid of it. However, you know, is that one of the things here that we must be very careful of here is that whatever the energy is going to come from here to actually run the motor car or wherever it comes from. The problem here, they did here some studies here some time ago, and what they found here's that look. We are here hyping up the electric car. But if you look at it now, electric cars is doing as much damage here as the internal combustion engine. What the electric car basically does, you know, the electric car here basically move the pollution here from in the city and move it what? Somewhere else, so you know affect you here in the city. Because the energy here that actually runs that electric car has to come from what? Somewhat. Where? And a lot of time the energy here that actually comes from what? The electric car. Why is this thing? Right, the energy here that actually comes from the electric car here is actually generated a lot of times here from what? The same oil, just that we have to move it what? Somewhere else. So we don't see a problem and we are basically not what? Solving the problem. Similarly here, they say here that the processes here actually involved in making those batteries for the electric car does more harm to the environment than, because when you look at where they mine them and what they do here, that is doing what? As much what? Harm. However, if we can in fact what convert here to our electric cars and we actually use what solar here to provide it, then that will be what a very cheap what solution, because solar here we have an abundance of it, so if we can use that, no problem, then we won't have to be relied. Or if the thing here which a lot of people here actually rely on here is actually what? Nuclear energy, right? Now nuclear energy here, true, it has its dangers, but it's also what? Extremely what? Cheap. As I say here in Jamaica, if we had a nuclear power plant, our electricity bill here would in fact be 1/3 what is we could actually enter, we could compete here worldwide here, we could have these huge factories and whatever. But the problem with that here is that nuclear power plants here, if we should in fact have an accident, then it is possible here that we could actually what? Wipe out a good part here of what? Jamaican, or we could kill here what? Millions of what? People. So what you find here?
Chernobyl.
Yeah, Chernobyl. Not only Chernobyl, what happened in not Chernobyl? Chernobyl is
So why
one.
not move it to the countryside?
No, but you still have a problem. Because look, one plant in Jamaica would pollute what? The entire what island. One plant, the amount of nuclear, the radioactive fallout here from one plant can in fact what? Do what? The entire what? Island could in fact do. And I don't think that you people are aware now. You know they have a small nuclear power plant on UWIC, on the UWIC
So yeah.
campus. Yeah.
Quite aware, sir.
Yes, they have a very small one. And what they are saying here is that if that one, if you in fact have an accent over this, so then you would have to what? Basically what? Evacuate all of what? Kingston, and you couldn't come there what? For years. So nuclear power plant, yes, it works good. It is what? Cheap, but the risks here are extremely what? Great. Now that is an argument here, you see, that people at university and whatever should in fact be putting what? Forward. Let us look at the pros and the cons here of in fact in the for development. Should we in fact go with a nuclear power plant? Because look, if we should in fact put a power plant in Jamaica, a lot of our problems here would in fact be solved. Don't get me wrong, we would solve a whole heap of them. We would be much better off in every respect. Our standard of life here would in fact improve. All these things here would in fact improve. But the problem is, are we willing to take the risk, right? The risk involved. Now, if you notice here in the developed countries, they have in fact taken decisions here not to make any new power plants. But only certain countries here are in fact doing it. Germany has taken decisions not to put in any more nuclear power plant. But the only reason why Germany has done that is because the leader, Merkel, is in fact a physicist. So if you put that decision here to a person here who is not a scientist, then you know where the hammer is going to come down on. It's going to come down, in fact, here say we're going to do whatever for development, which is the same argument here we are having now here in Jamaica with the Rio Buna. The mining here is actually in Rio Buna. The Prime Minister said that we need the money and we need the jobs here. But is it worth it here to actually destroy the habitat here for the few thousands of $1 million that we will get and the few jobs that we are going to create? Is it worth it to actually destroy that environment? I don't think here that is what worth it. Because part of the problem is that when the Prime Minister come out, you know that he's chatting a whole bunch of garbage. He jolly well knows here that when the project starts, it can't be lockdown and chatting foolishness about he's going to lock it down personally. Yes, he's going to lock it down, yes, when damage has already been done. And history has shown here that you lock down a project here for 2-3 days, and next 4 or 5 days, the project is back up doing the exact same thing, because we have no monitoring here to actually monitor. So he knows here that he's basically chatting foolishness. But for the price here of economic development, he is in fact willing to risk the habitat here in those limestone, the mountains. I see here that they have in fact now a petition here has in fact been launched for people here who should in fact sign the petition. If you sign it here, then it should in fact cause the government here to actually reconsider here what happens. But see, the basic problem we have with this now is the way here our constitution here and our laws here are basically set up. What happens here is that the law here basically says that after the EIA is done and the agency here that say, look, we shouldn't go ahead with this because it's going to destroy the environment, the government has the right here to overturn that, and we can do absolutely here nothing about it. All right, that is the crux of the matter. Because after NEPA said the project can go, it was overturned here by So one government minister to government minister sit down who don't know not about environment and made such a decision. So the problem here is really with the law here, that law here ought to be changed. So when the body here says it can't go, then basically here should not in fact go. All right, we have a lot of problems here, but we don't protect the environment here in Jamaica. I tell you something, I think New York here, you see, the water supply here for some part in New York here is that it actually comes from what a protected what area. And they say here that that area here has been protected for hundreds of years now. The water here which comes out of that place here is clean because they have made sure that there's absolutely what no development here in the area. It has stayed pristine as it was. In Jamaica, you remember what they did here with Long Mountain? We told here that look, Long Mountain, natural watershed here for the Mona Dab, because the politics it take Long Mountain and give it to what? A developer who go up there destroy all that environment already. So what? The price or whatever. So we in Jamaica here, we pay what scant regard here for our environment. But what happens, you know, is that it catches up with us a lot of times. So I hope you will reach the stage here like what has happened here in Haiti. Because in Haiti, you know, they have totally here disregarded all environment. They killed all the trees, they chopped down everything. So they are in what? Serious what problem. But it happens here in our third world here countries in that the protection for the environment here is extremely what? Weak.
Low regard.
Yeah, very little regard. Because let us face it, if you have the amount of money, can knock head with the minister and promise them things and give them money, then they will do whatever they can here to actually what? Facilitate. And that is what we actually have happening here what in Jamaica. All right, let us get back here to this conservation, right? Now, they said there are two ways in which energy here can be exchanged here with our surroundings, either by heat or by what rock. Because we can actually what lose heat, or we can in fact do what rock. Therefore, a change in internal energy of any closed system is equal to the amount of energy that flows into or out of a system due to a difference in temperature, plus the amount of work that flows in or out of a system as a result here of an applied what force. So just this principle here of conservation here of energy. We have a system. We put in energy here in our, or put in a certain amount of heat here in our system. So it goes in here. It can increase the internal energy of system, or it can in fact what do what work. So the energy here actually goes here somewhat where. Now this YouTube video here, please sit down and watch it here. Is really, it looks here at what the first law here of what thermodynamics is basically here what the first law actually goes into and explains here a lot of things here about what the first law here of what thermodynamics. Okay. Now we have some. Yes.
Can you post that link on the Edmodo?
It is in the. Yeah, man. It is on the Edmodo. This.
Okay.
Yeah, man. Yeah, man. This lecture is up, right? So look at it. All right. Now we have here some vocabulary here that we actually use here, and in fact, what looking here at what thermodynamics. We have here the isobaric process, which it basically means here that the pressure here is constant. Isovolumetric means that the volume constant, no work here is done. And we have the isothermal process, and we also have what the adiabatic process. So these are terms here which you normally what brand about here when we're in fact looking here at our thermodynamic what systems. Okay, so please here make sure you are in fact familiar here with these terms. A person using an isothermal process here, we basically know here what we're in fact what talking about. Now this here is a definition here of what the first law here of thermodynamics. As we said here, is that this here is actually the law here of conservation here of what energy. And what it basically states here is that the change in internal energy of a system equals the heat added minus the work done by the system. All right. Remember now the law says the work done by the system, not on the system. That's the only thing here we have to be what careful about, to identify here when work is done by the system as opposed to when work is done on the system. All right, so change in internal energy, U of a system equals to the heat added minus the work done here by what system. So we have here that delta U is equal to Q, the heat added by the system, minus W here, the work done by the system. And we use here the symbol here, delta U here, or U, to actually stands here for what? The internal energy of what system. So we have here that delta U, change internal energy, is equal to heat added minus the work done by the system. As I said, is a general reflection here of the law here of what? Conservation here of energy. Basically it says here that we put energy here in our what? System. Put the energy in our system, the energy here must in fact what? Go what? Somewhere. What the energy does here, it increases what? The internal energy, and it can also go into doing work here by our what? System. Now, internal energy, now also called thermal energy, is the energy an object or substance has due to its kinetic and potential energy associated with the random motion of all particles that actually what make it up. So when we talk about the internal energy, what we're talking about here is that the energy here that the atoms or the molecules here in our substance here basically what has. Now, the faster these molecules are moving, then what it means here that they will in fact have what? More what? Energy. More energy they have, it means here the temperature here will also be what? Greater. So that is what here we talk about when we talk about the internal energy. We're actually talking here about the kinetic energy and what the potential energy. Remember, the kinetic energy is actually given by a half m what? V squared. Putting energy in the system, what happens here is that V here actually what? Increases. So therefore the energy here must in fact also what? Increases. The hotter something is, the faster molecules are moving or vibrating, and the higher its temperature. Temperature is proportional to the average kinetic energy of the atoms or molecules that make up the substance. If, in fact, you're examining here the gas laws and the equation of state here, what we know here is that the temperature here is in fact proportional to the average kinetic energy here of what? The atoms, right? So therefore here, the higher the temperature, the higher here these kinetic energy of the molecule here basically is. Now, the internal energy of a substance or object can be changed in two ways, right? One, letting heat flow in and out of the system by substance doing work or having work done here on it. All right, so internal energy can change internally two ways: letting heat into or out of the system, and two, the substances here actually doing work or having work done on it. So in summary here, the change in internal energy is actually equal to the energy supplied minus the work here which is actually done here by the system. Now, as we said here, that Q is positive when heat actually flows what? In. W is the work done by the system, right? So the work system does work, and it means here that the work here is positive. If the gas expands because of added heat, it will do work by lifting here the weight up. Now, this work here would in fact be positive, and the work the gas does would decrease its internal energy. All right, so here the system here would in fact, they would actually be doing work. The work here would in fact be what? Positive. All right, so the work done on the gas now would actually be what? Negative. Let us now just look at some examples here of what happens here. We have a system here with a piston, and it is enclosed, and we have here a gas here at a particular pressure, volume, temperature, and here is actually what? The number of moles here of atoms or whatever we basically here have in our cylinder. P here is the pressure, V is the volume, T is the temperature, and N here is actually the amount of moles of substance, which is actually proportional here, the mass of our massing system. Now, as the piston here is basically moved inwards, right? So move the piston inwards. Now, if the container here is in fact insulated, the temperature here will in fact what? Rise. The atoms move faster, and the pressure here actually what? Rises. So what we have there now here is that the energy now, the internal energy here of the gas here basically here will in fact what? Increase. Because what we have basically done here is that we have basically reduced the space here that these atoms or these molecules here are actually what? Moving in. So if basically here reduce the space, what happens here is that they are going to be actually moving what? Smaller distances. So their speed here is basically here going to what? Going to be what? Increasing, or going to be getting a lot more what? Interactions and collisions. Now, the external agent did work in pushing the piston what? Inwards. Now, we know here that work here is actually equal to what? Force times distance. But we also know here that the pressure here on our system here is actually equal to what? The force divided by area. So what we know here is that the work done, which is the important thing here, work done here actually equals the pressure times the change here in internal what? Volume. Now, this equation here is very, very important. The work done here is actually equal to the pressure times the change here in what? Volume. And remember here that work here can in fact be what? Positive, or work here can in fact be what? Negative. So the work here is equal to P times the change here in what? Volume. Now the work done on the gas equals the change in internal energy. Work here is actually equal to the delta U, since no heat here enters, are in fact what? Left what? The system. All right, now let's change the situation. Keep the piston at its original position. Place the cylinder here on a hot plate. So therefore, we are now what? Putting energy here into our what? System, right? So when we put energy here into our system, then what it means here is that now the heat actually what flows into gas, atoms move faster. So the internal energy here of our system here basically what? Increases. All right? Now if we added heat and push the piston down at what? The same time, we added heat. Therefore here what? Internal energy here is going to what? Basically here increase, and we push the piston here further, the energy here is basically here also going to what? Increase at what? The same time, right? So work is done on the gas, heat is added to the gas, and the internal energy of the gas here basically what? Increases. Now, how do we determine the sign of work done from what? A PV diagram. So what we have here is that we normally draw here these PV diagrams of pressure against here, volume here for our substance. And from this now, what we want to do is that we basically here want to calculate here the work done. Now let's say our gas here starts in the state here of PV. Press the piston downwards, the volume of the gas will decrease, right? The volume of the gas here actually decreases. State here must in fact what? Shift towards the left, right? The volume here actually what? Decreases. Smaller volumes as seen in diagram. Since the gas is being compressed, we can also say for sure that positive work is being done on what? The gas. All right, so we're actually doing work here on the gas. So the work here done by the gas here would in fact be what? Negative. Now, what we have here now, we let the gas expand, pushing the piston here upwards. Then the volume will increase. The state must shift here to the right of larger here volumes. Now we can say that negative work is being done on the gas, and positive work here is being done by the gas. Okay, so the gas here is actually expanding. We have positive work here done by the gas. So therefore, no negative work is being done on the gas. So that's the distinction we have to make here. The distinction here between the positive work done by the gas and negative work being done what? On the gas. Now the work done during a thermodynamic process is equal to the area here under here our what? Graph. All right, so the work done here is equal to what? P times what? Delta what? V. The change in V here is actually what? The area here of this what? Rectangle. And what we see here is that the area of the rectangle here is actually equal to what? P times the change here in V. Pressure here is not in fact what? Changing. And the volume here would actually be what? Vf minus Vi, which would actually be equal to delta V. So the work done is equal to the force times our distance, which is equal to what? P times what? Delta what? V. Very important here for the work done is equal to what? The area under our what? PV what? Graph. Now we have to be really careful with signs throughout. If the part on the PV graph is directed to the left, the volume is decreasing and positive work is done on the gas. If the part on the PV diagram is directed to the right, as in diagram above, the volume is increasing and negative work is being done here on our what? Gas. All right, so now let us look at this. Suppose we actually had our PV graph that looks like what? This is not a rectangle. So therefore, we can in fact also now calculate here now the area here on our graph, right? We can do it here by using what? Calculus, or we can divide it up into small what? Triangles and in fact what? Do it. We are going to look at how we in fact here calculate the area here using calculus. It doesn't matter what the shape the part takes, the area on the curve will still represent the work done. For any curved part, we can imagine breaking it into an infinite amount of what? Infinitesimal what? Thin what? Rectangles. Now the important thing here with this here is that listen, you will not be getting a tutorial sheet here on thermodynamics. Is that you're going to be getting here questions here, and look here that we have a number of questions here which will in fact now discuss. So these will in fact be your what? Your tutorial. I say here that this, for this section here, what we are basically going to be looking at here is basically what? The first law here of thermodynamics. So all you need to do is know the first law and know how in fact what to apply here the first law. Now let us look at this example. It says here, a cylinder of radius 5.00 centimeters is kept at a pressure with a piston of mass, what, 75 what? Kilograms. And they give us some constants here. Tell us that atmospheric pressure here is equal to 101 kilopascal. Acceleration due to gravity here is actually equal to 9.811 meters per second. And they ask us now what is the pressure inside the cylinder. Now this question here is actually looking at thermodynamics, and is actually also looking at other aspects here of physics. So it's actually taking here a lot of some other areas here of what physics. Because what is basically saying here is that now, remember now, is that the pressure inside this gas here is actually due to what? Two things. Remember here is that it is due to what? Atmospheric pressure what? Pressing down, plus the pressure here that the gas here is in fact what? Exerting here in our what? Cylinder. So the total pressure here will actually be what? Atmospheric pressure. So the total pressure here will actually be equal to atmospheric pressure plus the pressure here due to what? The gas. So you can write here the total pressure is equal to what? The pressure due to the gas plus what? Atmospheric what? The pressure here due to what? Atmospheric pressure. Now what we know here that the pressure here due to the gas here is equal to what? Force divided by what? Area. Now the force here will actually be equal to what? The mass times what? G. And the mass here is actually equal 75 what? Kilograms times G, the acceleration due to gravity, over A here, the cross-sectional what? Area. Okay? Now we know here that what we are told here is that the radius here is equal to what? 5 centimeter. So therefore, we can in fact find what? The cross-sectional what? Area. Alright, so see here is actually what? The radius. So it's equal to 5.00 times 10 to the minus 2. Remember, the cross-sectional area is given by what? Pi r what squared. So when we do that, now we get the total pressure in the gas here to be equal to 1.95 times 10 to the 5th what? Pascals. Okay? So this here is actually what? The pressure inside the cylinder. As I said, remember, the pressure inside the cylinder here is actually due to what? Two things. The pressure here due to what? The atmosphere, which is in fact what? Pressing down. And also here, the pressure here due to what? Gas. Remember now, is that we are actually living under a sea here of what? Air. So the atmospheric pressure here that we basically here what feel is actually due to the air above, which is actually pressing down on us. Now we have become so accustomed to the air here that we basically here don't feel it, but we are actually under a tremendous amount of pressure here due to the air here that is actually what? Pressing down on what? On us. Right? Very, very what? Important. Now humans here, you see this thing here about atmospheric pressure? Depending on where in the world that you live, your body here actually what? Adapts here to what? Your environment. Now, if you live, the Africans here are the best what? Long distance here what? Runners. And what happens is that they actually live in the mountains here of what? The Kilimanjaro mountains. Now, when you live in the mountains, you know, because the air is less dense, you're under the pressure here that the air exerts on you here is actually less. What happens is that your lungs actually become bigger and more what? Efficient, because it has to now operate here at what? A lower pressure, right? So your body here actually becomes suited here to that environment. So if I take you from that mountain and bring you down to sea level now, you are going to outperform anybody here who has actually lived at sea level here for what? Any period of time. Because number one, your lung here is what? Much bigger, and it is much more what? Efficient. So it means that you can take in more oxygen and use a lot more oxygen than anybody here down what here, right? Now this affected here our footballers here when they went to Mexico City here to go play them football. Because what happened here is that in Mexico City, it is actually high up in altitude. So what happened, it showed them to be extremely what? Unfit. They could not in fact what? Compete what? With the Mexicans, because they were not what? Climatized here to the particular what? The climate. So there's no way here that they could in fact win them. Because if you are in that climate for a long time, as I hear that your body here become what? Totally what? Accustomed to that. So you actually perform what? Much better. All right. So what we basically hear is that the pressure here within a cylinder is in fact here due to what? Atmospheric pressure plus the pressure here due to our what? Gas. All right. And we know here that pressure is equal to what? Force divided by what? Area plus here our atmospheric pressure. Now the atmospheric pressure is normally 1.01 times 10 to the what? The 5th pascals, which is a constant here, which you don't need to know. Need to have some idea of what it is. So now we in fact have calculated now the pressure within the cylinder. So the pressure here is equal to 1.95 times 10 to the 5th what? Pascals. Now the second part says now if the gas expands such that the cylinder rises 12 centimeter, what work was done by what? The gas. Okay? Now we know here that the work done is equal to P times our change here in what? Volume. So what we need to do now is that we now need to find what? The change here in what? Volume. Now what we are told here is that we know here that volume here is equal to what? Cross-sectional area times what? Height. So volume here is given by what? Pi r squared here times what? H. So the change in volume here now would be equal to 3.14 times 5.0 times 10 to the minus 2 squared times 0.120, which is in fact what? 12 centimeter here that it actually what? Rose. Okay? So now we can in fact work out now the work done. And the work done now would be equal to the pressure, which is equal to 1.95 times 10 to the 5 divided, times here our what? Change here in volume, and the work here actually comes out to be 184 watt joules. Now people, this question here, let's say here is a very important one question. And the reason why this question here is very important, and you're going to see this question again, is because it actually entails here a lot of what? Physics. It's not only one thing here involved in this question here, but actually takes in here quite a lot your knowledge here of what? Physics. All right? So number one, it is testing to whether you know here that atmospheric pressure. Is also testing here that you basically know here the pressure is made up of what? Atmospheric pressure plus the pressure within the cylinder. And it's also testing the fact here that you must know here that pressure here is actually equal to what? Force divided by what? By area. Okay? And it's also testing the fact here that you must know here that the cross-sectional area is given by what? Pi r what squared. So I said here that this question here is a very what? Good what? Question here. You actually have to do a lot of things here to actually what? Arrive at the answer. It's not a one-step process. Involves here a lot of processes here. Now the other part now is asking what amount of work went into changing the gravitational potential energy here of what? The piston. Now we know here that work here is actually equal to what? The force times our what? Distance here actually what? Moves. So the change in gravitational potential energy here would actually be the force here, which is equal to 75 times 9.81 times the distance here, x, 0.1, to actually get what? 88.3 watt joules. All right? And the other part of the question is asking, where did the rest of what? The work go? The rest of the work here actually went into actually what? Compressing here the external what? Air. All right? It actually compresses here the outside what? Air. So I said here that, look, this example here are very good examples, very good example. It draws here a lot of other physics knowledge here into here the what? The question. It's a very, very what? Good question. Now here we have some examples now, a straightforward here now application here of what? The first law here of what? Thermodynamics. And for these here, all you need here is actually to make the distinction between work done by the system as opposed to work done on the system. It says here 2,500 joules of heat is added to a system and 1,800 of joule of work is done by the system. Right? So it says by the system. What is the change in internal energy here of the system? So what we do here is that we basically here write the formula, which says here that change in internal energy is equal to what? Q minus what? W. All right? Now, we add work to the system. That means that Q here is in fact what? Positive. And the system here now does work. So it's done by the system. So we actually have what? A negative sign here. So actually have, so the work done by the system here in this case here is in fact what? Positive. Remember, when work done by the system, it is positive. So therefore, the change in internal energy here is actually equal to what? 700 watt joules. All right? So all we're doing here is that we basically, all we need to be able to do is actually to distinguish here whether work is done on the system or work is done by the system. What sign you put in our equation. Right, so we write our simple equation, and now that's the only decision here that we basically have to make, whether work is done on the system or work is done what? By the system. Now, for example 3 now, it says 2,500 joules of heat is added to a system, and 1,800 joules of work now is now done on the system. So we are now basically doing work on the system, not by the system. All right. So since work is being done on the system now, it is now equal to what? Negative. All right. So our equation now is change in internal energy is equal to 2,500 now minus 1,800, which is actually equal to what? 4,000 what? 200 watt joules. All right. So that is the important distinction here, which you actually need to get what? Clear whether work is in fact done by the system or work is being done on the system. Now we have another example here, is that a gas is enclosed in a container is heated, causing the lid of the container here to rise. The gas performs 3.0 joules of work to raise the lid, such that it has a final total energy here of what? 15 joules. How much heat energy was added here to what? The system? Basically here we just what? Write our formula, substitute our formula, and we in fact here get that we actually get 18 joules here, which are in fact what? Added. So all we are doing here is that we just applying this formula here, we state that what delta U here is equal to what? Q minus what? W. That is all here we are in fact what? Doing. All right. This one here is basically here what? This exact same thing. We're in fact here applying here our what? Formula. Exact same thing. So I want to look at these questions. I said that all you have to do here is that you just have to make the distinction here between whether work is done by the system or work is in fact done on the system. That's the only thing here you basically have to do here in these what? In all of these the problems here that we're in fact what? Looking at. All right. This one here, we in fact looked at the answer here when we're in the earlier part of the lecture, because here use the first law of thermodynamics to explain why a closed fixed volume container gas increases in temperature when heat is in fact what? Added. Now we add heat to what? The gas. So if we add heat to the gas here, then the energy here can only go into two things. Either we can increase what? The internal energy, or it can actually go into work, or it can actually do what? Both at them. All right. What the first law basically says. All right. Similarly here, what I think here is in fact what? Cool. That means here is in fact what? Losing what? Some amount of energy. Now remember here is that the first law of thermodynamics here, what it deals with? The conservation here of what? Energy. Talking about the first law of conservation, just another way here of in fact what? Stating here the law of what? Conservation here of what? Energy. Now this here now is actually testing here to see whether you can in fact write here the first law here of thermodynamics. That is not right, that's not right. So the first law of thermodynamics is internal energy equals to the heat added plus the work done by the system. Now, people, please be very careful here with these what questions, because then it could be heat added plus the work done on the system, and that would in fact be what? Incorrect. All right, so it's actually work done here by the what? The system. Now, this question here also here are the what? Straightforward here application here of our what? Third law. So all of these questions here, what we are basically doing here is that we're going to write the formula, we're going to substitute the numbers in it, and we are going to come up here with a basic come up here with an answer. Okay? So you please look at those questions. Now this one here is actually testing. It says here, what is the name of the following statement? When two systems are in thermal equilibrium with a third system, they are in thermal equilibrium with each other. And this here is actually what? The zeroth law here of what? Thermodynamics. This is what the zeroth law here basically what states. Now this one now, which statements is true about the first law of thermodynamics? Energy cannot be what? Created. That is, it says that's true. Energy here cannot be destroyed. That's also true. We never said nothing about energy being destroyed. It's another name for the conservation of energy. That is also true. So in this case here, all of these statements here are in fact what? Correct. Right? Because the law of conservation of energy, we can create energy. We can destroy energy. And it is that same thing here as the law of what? Conservation here of energy. So in this case here, all of these statements here are in fact what? True about the first law here of what? Thermodynamics. All right, now I have wrote this one. It says a gas in a closed container is heated with 10 joules of energy, causing the lid of the container to rise 2.0 meters with a what? 3.0 Newton force. What's the total change in internal energy here of the system? Now you notice here is that with this one here now, what we have to do here is that we actually have to work out all the work here which is done here by what? The system. Because what they have given us here is that they have given us a force here and what? A distance. So therefore, what we have to do here is that we have to work out the work done first before we can in fact what? Apply what? The first what? Law. Okay? So therefore, our first job here is actually what? We're not given a value for the work, but we can solve it by using the force and distance. Now, work is the product of force and displacement. So we have here work here is equal to what? Force times distance. The work here is actually equal to what? 6 what? Joules. And what we have said here is that we have added 10 joules here of energy. So therefore, the change in internal energy here would be equal to what? 10 minus what? 6, which would actually be equal to what? 4 what? Joules. All right. So here, remember now, it says here, and the lid of the container what? Rises. So since the lid of the container here actually rises, what happens here is that the gas here is actually what? Doing what? Work. So work is being done by the gas. So since it's work here is actually being done by the gas, it means here that this 6 here will in fact be what? Positive. So that is why we actually have a negative sign here. All right, all these here are basically the same thing, so you can actually look at them. All right, let us look at this now involving our PV graph. We haven't looked at any here which is actually involves a PV graph. So what we have here is that we have a graph here for what? Pressure against your volume for a process here, which is what? AB what? CD. And we're not even going to define here what cyclic processes as opposed to what non-cyclic processes are that. So we're not going to go in so much detail. All right, so it says here, where 1 mole of an ideal monatomic gas runs through a 4-step cycle. Our processes are either isobaric or isochoric. Calculate the work done here by the gas along what? AB. All right, so from A to B now, it says what? The work done by the gas. So from A to B here, the work done by the gas, it will actually be equal to what? P times what? V. Now along BC here, along from B to C, the work done by the gas here will actually be equal to what? 0 here, because what happens here is that the volume here is not what? Changing. Our work here is actually P times V. We can also calculate the work done here along what? CD. Work done along DA here, that will also be equal to what? 0, because the volume here is not in fact what? Changing. Remember, work here is equal to P times V. So if V here does not change here, then no work here can in fact basically here be what? Be done. All right, so that is what here we actually come up here with our what? Solution. Work done here from A to B. That is now from A to B, which is equal to 0.06 minus the 2 times our change in what? Pressure. So for this one here, you actually have to now look at the graph, read the values here from the graph, and then you actually do your what? Your calculations. And now this one here is the final one. It says here, an ideal gas in a sealed container is taken through the processes shown in the PV diagram. Initial volume of the gas is 0.25 meters cubed. Final volume 0.75 meters cubed. Initial pressure of the gas is 70,000 pascals. Final is 160,000 pascals. What is the work done by the gas during this expansion? Now remember here that the work done is actually what? The area here on the our graph. So what we are going to be doing for this here is that we are now going to be finding, first we're going to find what? The area here of this what? Rectangle. All right. Area here is equal to what? P times V. Then we are going to find the area here of that triangle. We're going to add up both of them. And the answer here that we are supposed to get here is equal to what? Negative what? 57,500 what? Joules. All right. So remember it says what's the work done on the gas. So since we're talking about work done on the gas, then it must in fact be what? Negative. If we're talking about the work done by the gas now, then this answer here would in fact be what? Positive. All right? All right, that here completes here what we have to do here with what? The first law of thermodynamics. So what you have to know here is that number one, you have to be able to what? State the first law of thermodynamics and do any one of these simple problems here involving what? Thermodynamics. The questions here on the exam are going to come directly here from this what PowerPoint. There's going to be nothing here which we in fact have not covered here in our PowerPoint. And for persons here who know here or understand here how people set exam questions here, you can look at this PowerPoint here. Since I tell you here that maybe 3 questions are coming from it, you can look at it and see here which 3 questions or 4 questions I'm going to be taking here from this what? From the PowerPoint. You are not going to be getting what? The very easy ones, but you must have idea here of the ones here that you can in fact be able to actually do. All right? Why this thing here not updating properly?
Sir.
Yeah.
You're saying for the test next week.
Yeah.
From what topic again? From damp harmonic up to now?
No man, you're not getting the science test in the next week in the bus. We're getting up to what we did last week, which is thermal concept. This is not on the test next week.
Okay,
right?
this is for now.
Right. So you're not getting this on the test, right? So you have ample time because no, this week what you are going to be doing here is that during your lab session this week now, you're going to be doing the questions here in the back here of your handout here on thermal what? Conductivity. So there are some questions here on thermal conductivity here on the back of the handout. So that is what you're going to be doing in your laboratory sessions here this week. So for the test next week now, everybody here will in fact have completed all the tutorials here up to what? Thermal what? Conductivity. All right, and I'm going to give you a test here if you basically have not looked at the tutorial, and we wouldn't have time here to actually do a tutorial here on this. Okay, so this year is not basically going to be in the test.
So what I wanted to confirm was from where again?
Yeah, man. All right, it is actually from waves. Because remember, the last test here was actually up to what? Damped harmonic motion. So from, we have left that topic now, up to thermal conductivity. All right? So that is...
All right. You confirm the date?
Yeah,
the specific date for the final yet?
No, I have not. No. That here is kind of still giving me a problem here as to exactly how that thing here.
I have one next test on the 5th, so can't be the 5th.
When you have one on the 5th?
Yeah, that's a Saturday though.
Oh, it's a Saturday? No, me not giving mine on a Saturday. All right, what I want at the end of this week, then I have to have a answer here for you. If not, which I don't want, if not here, it means here that if we can arrive at a final date which is convenient to everybody, it means here that we'll have go do your test here during your class time, which I didn't want because it will require you setting too much. It's too much test that if you actually.
I don't really mind the class time test.
Huh?
The class time test, all right.
Yeah, no. All right, but let me tell you what the problem here with the class time test. If the class time test, now what it means here is that I have to do too much exams. That's what it means. Because you could do one exam here for the Monday, one exam for the Wednesday, and one exam for the Thursday. So I would really like you to have it on one day so everybody come in and do it one day. But the problem I'm asking here, you people, I spoke to somebody here and they were telling me here that the student union here was actually meeting with the administration here over the same thing here of what, the dates of the test or whatever. So they should in fact have some meetings last week, but the person has not come back to me and tell me what has in fact come out of that meeting. Because the problem here that we are going to be running in here is that you might be having what, 2 tests and 1 day or test what, back to back. So in order to alleviate that problem here, what should in fact happen here is that a exam timetable here should in fact be generated. So you know here that look, you're doing this exam at that time and that and the other time. And people here don't go about and arbitrarily set the exam because I can arbitrarily set my exam to the 5th or the 6th now. And if you clash with your one, you understand me? So we don't want that to happen. What we basically want here is that you actually don't have 2 exams one day, if we can spread it out as far as possible for you to get what? The maximum chance here to do the best in what? In your exams. But as I said here, student union was supposed to meet with admin to see. I have not heard what has come out of that meeting, so I'm kind of waiting on that to see exactly here what is going to come out of that. Okay, so I hope you will in fact step in and don't leave everybody here to actually set the exam when they feel like or whatever. That something concrete can come from that, so we can have everybody here can in fact feel comfortable with the times here of the test. All right.
Yeah, sir. The test next week, it will be done in the lecture session, right?
Yeah, man. Yeah. That definitely isn't. Yeah. That definitely isn't the lecture session. Yes. So I can say conclusive that is being done in the lecture session. All right. Any other questions?
Sir?
Yeah.
Sir?
Yeah, man. Go on.
Sir, I emailed you about the switch from group 3 to group 1, sir, but I haven't gotten a response as it.
I haven't reached. What's your name? What's my name? So I can make sure. What's your name?
Dev Mario McDonald.
Dev Mario. And you say what you want to be shifted from what to what, sir?
From group 3 on the Edmodo app to group 1.
Oh, from group 3. Oh, all right. So, okay. Group 1 in mode. All right. So I will make sure say then that is done for you here, Mr. Demario McDonald.
Yes, sir. Dev Mario. DEV.
DEV MAR
MARIO. Yes, sir. Dev Mario.
Mac MC what? UNLD.
Yes, sir.
All right, fine. Okay, Mr. McDonald, I will in fact do that. Make sure it's done today too. So because all right, now for the persons here, you see our persons here who are in fact repeating the course here who have lab grades here. Next week here, I will in fact send you something here so you can in fact tell me here the persons here who are in fact doing it so I can in fact make a note. I do ready to deal with the exemptions here from the lab. Okay. So if you have that, please hold on to it. I'm not dealing with that right now.
It's safe to say that the labs last week was the last lab, right?
Yes, sir. But this week you're going to the lab, right? This week you're going to the lab. I'm going to do a tutorial. You're going to do a tutorial here on thermal conductivity. Yes, sir. Right.
All right, well, thanks.
Yeah, right. All right. Any other questions?
I kind of missed it. You said that the cycle here isn't important, right? For the solution on the screen right now, knowing the cycle not important.
No, we're not looking at the cyclic process. Yeah, we're not looking at it. We're just looking at the work done just in the individual parts.
Oh, okay.
Yeah, we're not looking because you have to here that we can look at what the cyclic process. No, we make it simple. We're not doing that part. Yeah, we're not looking at the cycle, whatever, and the complete process. Yeah.
Nice and simple.
Yeah, man, nice and simple. We're not going to complicate things. Any other questions? Any other questions, people?
No, sir.
All right. Well, everybody, I wish you all the best in your test next week. Please sit down, put pen and paper, and try to work the problems I'm asking you. Please sit down and please do that. All right?
Oh, sir, one more quick question before you go. The lab session this week, it still would be counted as a lab.
No, it won't count as a lab.
It won't be counted as a lab.
No, because the work you do, the work you do here will not be handed in to be graded. It's for your own benefit now. If you have any questions, you have any thermal conductivity, then that's the time you have to do it, right?
Oh.
All right. So the lab session here, what you are doing this week, I expect you here to look at the handout, and if there are any questions in whatever, then you go to your lab, then you ask the person here to. That is what it is intended for. Okay. So you actually have more time to do this tutorial than the other tutorials because now the lab session is 3 hours. So you have ample time here to do everything on it, right? Everything on it, okay? So please use the time wisely, okay? And don't, because I don't have a lab, you don't buy a turn up or whatever. Use the time wisely. I'm begging you. All right?
Sir, one more thing, sir.
Yeah, man, go on. Mm-hmm.
Sir, for last class, my light been gone halfway through the class, so I'm not sure if I did go on the register.
All right, that is not a problem. A problem here, sir. Because no, all right. The way the register is done, right? Your name would in fact be there. Because if you had logged on here, so within the first half an hour or whatever, then it would in fact be recorded. because this new attendance here, which it has, which is a brand new one, what it actually does is actually record the time here when you come, and if you leave and you record and you come back again, if you come and leave 20 times, that will record that you come in that time, you left and you come in that time. But if you are coming initially here, then it will in fact be recorded. All right, sir? So that is nothing to worry about.
All right, sir. Respect.
Yeah. Man. Any other questions? Any questions from anybody? Any concerns? Please talk up now. So give me a chance to talk.
No, sir, look more.
So log into class prior to the test, right?
Huh?
Next week for the test, you must log into the class first. I just show you that test.
No, man, you will log into Edmoodle as you did. You could log into your class before having anything to and then you go on that. Oh, one last thing. I have received a request here from the dean or whatever. So they are requesting some extra classes, your extra class on the 27th of November. Anybody here know about that class here or whatever is supposed to happen?
No, extra class.
Have the student union said
No,
anything?
no, sir. First, I hear about that.
Eh?
First, I hear about that.
Yeah,
The 27 is a Friday, sir.
yeah, I know. Is that Friday? Yes, man. Is that Friday? Is that Friday?
Sir, you confirm said the lab grade at 30%?
May I say that is 30%.
May I just ask again?
Yeah, man. Yes, yes.
Sure.
Yeah, man. Yeah, man.
Last time I asked
Yeah.
again, sir, me the last week.
No, man. It's 30. It's 30. Well, all right. I'm going to get back to you here on that class at that time. All right. Now, I am not adverse here to having an extra class after we have finished class next week, but we can talk about that next week. Okay. So if you have anything here special, then we can have another session here where anything and questions here, I will be willing to answer you. Okay. So
Sir,
next week
sir.
you'll talk about
All right,
If the
sir.
lab grade is 30, is how much is the final?
30.
All right.
Yeah, man.
Sir, how communicate? This would be our last class, right, sir?
Last official lecture class. Yes, man. Yeah.
Official lecture class. So how would
Yeah.
communication going forward be done? Same Edmoodle?
No, use my email.
Okay.
And the group.
Yeah.
Um,
Email.
Will we host or what am I saying now? Will we know our final coursework
Yes.
grade before
Yes,
the
sir.
final?
Yes, sir. Yeah. Watch me now. You by before the 11th of December, then you'll know your coursework, everything you are going to know before we actually put it up on the official university system, right? So you'll know it before that, right, sir?
Yes, sir. The 11th of December.
Yeah. I finish everything by the 11th of December.
The final exam is we're not talking about the final grade overall. I'm talking about the coursework grade before
Yeah,
the
man.
final.
Yes, man. Yes, you are going to get it. Yes. Yeah. Because when the second test done, then I'm going to put up a something with both ends. So you look at it and make sure you say it right.
But they said the 11th of December and the final will be in the first week of December.
No, hold on. No,
Sir, the 30th of the final.
no, man.
That's it, the last.
That week. During that week.
So we will know the coursework grade.
Yes,
before that.
sir. Yes.
Alright.
You will know your coursework grade here before that, so you know what grade you're going into the exam with. You have to, by that time, you have to know what your coursework grade and also your lab grade, so you know exactly what grade you're in fact going into it with. So I suspect a lot of persons here are going to even pass here before the final exam grade. Even before the final exam grade, then I say me pass it already. Because So what?
I mean, so they don't have to do the final then.
Yeah, that's true. They don't have to do the final.
Sir, may I say hello? Good joke, man.
No, it's true.
The person.
It's true. After do the final, you can go and go spend 10 minutes in the final and say, me gone. I am passed. The team going to go to the most pass. Me can't feel impossible.
Well, sir, just hope that we get the grades before the final.
No, man, no hope. You don't know hope. No hope, Mr. Whatever. You don't know hope, you have to get it. You don't know hope, you'll get it. You don't know hope. You don't know hope, you will get it. Then if you don't get it, then you know if you call me every day, or every 10 minutes you call me and say where the grades are, alright?
Alright, boss.
Yeah, man, so you do that. It is your right to know it. Alright, any other questions? Alright, if you have no other questions, Have a good week and please stay safe. So next week you're doing this time, you'll in fact do your what? Your second what test. All right? Okay, people.
All right, sir.
Okay, bye.
Oh, yeah.